Hello everyone. Assalamu alaikum. I am Mr. Rimon from United International University, Bangladesh. So in this tutorial segment, basically what we will see. So welcome to all of you to in this tutorial segment. So in this tutorial segment, basically we will see that the NMOS characteristics and analysis in Cadence Virtuoso. So without wasting any of time, let us proceed. So in the schematic editor, I already sketched this schematic. I am using here GPDK 90 nanometer and MOS 1 volt. And you can see the schematic diagram. I consider here two DC voltage source and make the length of this MOSFET as a variable and width of the NMOS as a variable. So apply. So this is the gate, this is the drain, and this is the source, right? So the body and the source will be short togetherly and do it ground. So we will apply here a gate voltage, a DC voltage. So this gate voltage also a variable, VG. VG means gate voltage. Also, I am applying here DC voltage, which is VD. So VD means drain voltage. So up to now, this will be fine. Check and save. Then launch the ADEL. So we define different type of variable in our schematic. So we have some design variables. So let's copy from cell view. We can see our design variable here. So let me just serial those things. So at first I will give some value here. Suppose for 19 nanometer technology, the minimum channel length will be 100 nanometer. So I'm using here 100 nanometer and the minimum width is 120 nanometer. So let us use here. So VD and VG we don't know. So let us consider some arbitrary value. Let's consider VD is, for example, 0.3 millivolt. Sorry, 0.3 volt. So it means 300 millivolt. And VG will be, let's say, 0.7, or you may consider 0.4, whatever. Apply OK. Fine. Now we will do analysis. So at first we will do the DC analysis. So go to the DC analysis, and from the DC analysis you select the DC operating point, and we will sweep our variable. We will sweep variable. Why we sweep our variable? Because we want to try to plot the ID versus VDS curve. ID versus VDS curve. So we will select the design variable, and the variable will select here. So VD is our variable. Okay, so click OK and start from, let's say, 0 and stop um, 1, 0 to 1. So click apply. Okay. So before run the simulation, let's check the model libraries. Okay, so this is 19 nanometer. Okay, fine. So click OK. Now run the simulation. All right. So if you see the Virtuoso, your simulation complete successfully and no error. Okay, so now we want to plot actually ID versus VDS. So we need actually ID. So how do we get ID? So let's go to tools and find out the calculator. So click on the OS. So what is OS? Select a schematic signal and then choose a DC operating point to create an expression to sweep the selected point. So now we select our MOSFET and click on the list. So you can see that this is our ID. So we need our ID. So click it and now send it to the buffer expression. So we get ID. So now let's run the simulation. All right. So you can see that your x-axis is your VDS, your drain voltage, and your y-axis is your current or your drain current, which is ID. So what you can explain for this from this curve? So you can explain from this curve that is, if you increase your drain voltage, your current will be increased, right? Your current will be increased. So you can see that we will increase our drain voltage. So we can see that our current is actually increased. So this is the first observation. But we want to actually now say that let's fix our VDS. Let's fix our VDS, for example, suppose 400 millivolt. So in this case, our current is 8.22148 microampere. But now I will give you a challenge. That is, your VDS is fixed and your current is 8.221 microampere. Please increase your current. Please increase your current with this 400 millivolt VDS. So what you will do in these cases? So now I will explain these things in details. So as it is, you can see that my VDS is setting to the 400 millivolt, for example. So now I will do parametric analysis and I will actually select a variable. My gate voltage is my variable. So initially I give 0.4 volt as my gate variable, sorry, my gate voltage. So now I will sweep my gate voltage from 0 volt to 800 millivolt and consider step size 5. Now run the simulation. Okay. So now what you can see we can see that we accept our challenge. That is, initially you have a VDS which is 400 millivolt, which I maintain here, and you have a current which is roughly 25 microampere most probably. The challenge is that you cannot change your VDS, but you will increase your current. So you can see that my current is maximum now, which is 43.3287 microampere. So how do I get maximum current with the same VDS? Let us discuss about that. Here actually I change my VG, that is my gate voltage. So if you see that whenever my gate voltage is 0, that is under the threshold voltage of my MOSFET, the MOSFET is actually turned off and the current is actually negative sometimes positive, but the value is actually nanoampere range, which is negligible amount of current or leakage current. And in this case, your MOSFET is operating in cutoff region. That means your MOSFET is actually off. Under the threshold voltage, your MOSFET is actually work as a cutoff region. Now, you will increase your gate voltage from 0 to 200 millivolt. So what you can see? So you can see that for the same VDS, your current is now increased. So your green curve is for 200 millivolt gate voltage. You get 406.025 nanoampere. Your current is a little bit increased. Now, if you increase the gate voltage furthermore, like 400 millivolt, you can see that for the same VDS, your current is actually increase more. If you increase more VGS, our current is increased more. If we furthermore increase our VGS, like in this case we use here 800 millivolt, we get 43.3287 microampere current. So we change our VGS, but we fixed our VDS, we get higher current. So if we change our gate voltage and let's say VDS is fixed, so in this case we get higher current. And interesting thing is that if you see that for lesser drain voltage, like for example 100 millivolt, 0 to 100 millivolt, in this range. So in this range, this portion of this curve is basically comes from origin and it seems like straight line. If we further reduce the drain voltage, for example 60 millivolt, for a good understanding, 60 millivolt. So just this region. So what you can see, first observation is that your drain voltage is reduced, your current is reduced. This is the first observation. But still, for a higher gate voltage, you get much current. For lower gate voltage, you get lesser amount of current. But important thing that I want to explain, that is from 0 to 600 millivolt in this region, this portion of the curve is basically look like linear. Linear means it actually follow the y equal to mx curve, that is origin going straight line equation. That means linear curve. So what does it means by the linear curve? It is actually the characteristics of a resistor. So in this region, your MOSFET is basically work as a resistor, and this region is called as linear or triad region. So in this region, you basically apply very lesser amount of drain to source voltage. Whenever your drain to source voltage will be very lesser, in this case your MOSFET will be work as a resistance. Your MOSFET will be work as a resistance. But if you increase your drain to source voltage furthermore, for example, like here 250 millivolt. So in this region, or from this point to this side, right side, this region, the current is actually increasing, but the current is actually not increased linearly. You can see that the current is actually changed drastically. Drastically means that it cannot change with linearly. If you consider here a slope, you cannot find linear relationship. You will find a different slope for this curve. So in this side or in this region, your MOSFET will work as a amplifier or a current source or maybe diode connected load. So this region is called saturation region. So we have basically three region here. So number one, we have cutoff region. So this is the cutoff region where when we get cutoff region, our MOSFET gate voltage is less than below the threshold voltage. In that case, we get the cutoff region. Whenever our MOSFET gate voltage is greater than the threshold voltage, the MOSFET will turn on, but it will depends on the drain voltage. If the drain voltage is very smaller, like in this case 100 millivolt or 60 millivolt or 70 millivolt, in this range, this region, your MOSFET will work as a resistor, and this region is called linear or triad region. And after that, if you increase your drain voltage furthermore, you can see that your region of operation will be changed, and this region is called saturation region. And for a specific drain voltage, for example 400 millivolt. So for a specific drain voltage, if you want to increase your current, you can increase your gate voltage. If you increase your gate voltage, then your current will be increased. So that's how this curve is actually work. In the next tutorial video, I will explain furthermore many things in details and analyze the curve in more. So I think this will be enough for this time of this tutorial video. Unless I stop the video here, the video length will be very much or very big video, so people cannot be patient and try to see the video of a big length. So with this, I conclude this tutorial. So thank you everybody.